All right. Hi there, everyone. Thanks very much for having me. My name is Kristin Siu, and today I'm going to be giving a talk for PROCJAM 2017. Today I'll be talking about a project that I'm currently working on for procedurally generating boss encounters in games. So before we get started, I'd just like to give a quick disclaimer. Note about me, I'm currently a PhD candidate at Georgia Tech, a software engineer at Microsoft, and an independent game developer working for Golden Glitch Studios on a game called Elsinore, a time-looping Shakespearean adventure game about Hamlet. Today, however, I'm going to be putting on my PCG hat, and I'm going to be talking about an independent project that I work on in addition to all of these. So just to be clear, none of the work that I'm speaking about today is affiliated with Georgia Tech, Microsoft, or Golden Glitch Studios, nor am I speaking as a representative of any of these institutions or companies. So today I'm going to be talking primarily about procedural content generation in the context of games. For those, I know a lot of you out there are not necessarily involved in game development, but a lot of the things that I'll be talking about today might hopefully be able to apply to interactive media and other kinds of artifacts in general, so I hope that you find this inspiring and a little bit fun. So let's start out with some things about games. So many of you are probably familiar with all the wonderful things that we've been able to generate procedurally for games. So worlds, levels, the stuff in those worlds and levels, things like trees, because nobody wants to model dozens and dozens of trees by hand. Weapons, weapon names, character names, procedurally generated stories, narrative, full-blown experiences, you name it. We've been able to generate a lot of this. But there are also some things that we haven't been able to generate, and today I'm going to be talking about one of these, which is what about bosses? So, boss encounters, boss fights. I'm going to be using the terms interchangeably today. Let's talk about them. So here we've got a lot of boss fights that many of you may be familiar with. So boss fights in games are fantastic. There are these climactic, intense moments that provide challenges, and then they're designed to test the player's skill or knowledge of the game mechanics. Often they gate the player's progression through the game. They're these super intense moments that often tie into the game's narrative or are used to drive the story. They're often accompanied by epic cutscenes, rocking music, flashy aesthetics or special effects or unique mechanics for the particular part of the experience. And basically they're intended to be these super memorable instances of gameplay that, you know, are often the things that players talk about for years to come. And sometimes they talk about them in a good way, sometimes they talk about them in a bad way. It all depends on how the fight actually gets implemented and turns out. So these are the kinds of things that we want to generate. And it's not easy. In particular, it's hard. So just creating a boss fight to start with is difficult. These boss encounters are these handcrafted, asset-intensive experiences with a really high production cost. Often they require unique mechanics, special music, special assets or models, and a lot of fine-tuning to get right. When it comes to the players who are actually playing and experiencing these fights, boss encounters are some of the most subjective and occasionally polarizing parts of a particular game. Players have a lot of really strong opinions about what makes a boss fight good or bad, and they're very vocal about these, as it turns out from this quick YouTube search. So if we want to generate them, we have to take all of these things into account. But wait, Kristin, you say, isn't that just palette swapping? We've already done this before. Yes, it's true. So, you know, one first step when thinking about, you know, what procedurally generated bosses might look like might be something like palette swapping. And it's true that bosses are often palette swapped or reused because they're so expensive to create. Sometimes different versions of bosses are given different attacks and behaviors. But the thing that I want to highlight is that it's still expensive to make these. Somebody still has to go in and insert or implement every single new attack, every single sprite change, and yes, you can reuse these enemies, but you still have to do a lot of work for that. And we don't necessarily want to do that much work every single time we want to add a new boss to our game. So before we jump into the actual generation and what it all means, I want to define what precisely I am talking about when I talk about a boss fight or a boss encounter. So here's a picture of a boss fight from the game Metroid Zero Mission. And so what are the components of this experience that we're going to be looking at? So first, there's this idea of the player character. This is the avatar through which the player acts. The player has access to some set of combat mechanics. So in this particular example, there's this notion of health. There's this notion of having extra equipment or abilities, which in this case are missiles. And this is what the player comes into the particular experience with. Facing the player is some kind of entity. In this case, it's a space pirate boss called Ridley. Ridley's components are first its morphology. So what physical properties does the boss have? What space does it take up? How fast does it move? How much damage does it do? And there's also a set of behaviors or actions that the boss can take that it's allowed to use and it uses to interact with the player. And in addition to all of this, we can't forget about the particular environment where this experience is taking place. The environment also has its own notion of morphology, which is the pieces and the walls, the ground, the obstacles in the way, and also may have some reactive behavior of its own. So in this case, the environment is not particularly reactive, but that lava at the bottom can damage the player if the player steps into it. And so when I'm talking about what exactly we want to generate, let's, for simplicity, fix the player and the combat mechanics now. So often, if you might think about generating boss, you probably have some idea of what you want the player and the mechanics that the player is allowed to use to be. So if we fix that, then what we really want to concentrate on generating is the boss's morphology, the boss's behavior, and the environment that it takes place in. So as I mentioned before, bosses are these extremely complex, high production, super expensive kinds of experiences. But when we look at the kinds of fights across different games, and here we're looking at fights in 2D games. Yes, I understand that I showed you a screenshot of a 3D game that was Shadow of the Colossus, but first, 3D games are hard, so let's look at 2D games. There are a lot of, if we sort of look at all of these games together, there are a lot of things that are pretty similar about them. And so if we just pretend that everything is just a bunch of moving shapes, we might notice that, hey, it's just a bunch of shapes moving around on the screen and different things are happening, and what happens tends to differ based on the mechanics of the game. But for the most part, we might be able to generalize this. So I'm going to formally state the boss problem again. So first, let's focus on 2D action adventure games. And we're specifically going to focus on games with the following properties. So these are games that have real-time movement in a continuous space. So we're not looking at turn-based games. We're not looking at grid-based strategy games. We're looking at things where the player has a continuous axis of movement. These games also tend to have things like kinematic physics, and often these physics objects in the space often interact through collisions between static and dynamic objects. There's notions of things like hurt boxes and hit boxes that the players can do damage or take damage from. And the entities in this world are often state-based, and they cycle between behavior. So bosses have things like attack patterns or sequences of attacks, and often these tend to cycle or they rotate through them. And so again, what we want to generate is the boss's morphology, so the state and the parameters that are associated with it, the behavior that it takes throughout this fight, as well as the environment that it takes place in. So what do we need to do to make all of this work? So I'm going to outline 4 pieces to sort of a pipeline, or at least the way that I like to think about this problem, which is first we need to think about the representation. So in order to generate anything, we need to know what exactly we are generating. And so how do we model boss encounters? Once we're able to do that, we can start generating boss encounters. And so then the question becomes, well, what kind of algorithms or techniques can we use to generate in our given representation? Generating is all well and good, but at this, we can generate a lot of stuff, but we need to be able to evaluate how good it is. So how do we ensure that these boss encounters that we're generating meet some criteria that we care about? And once we're able to do this, well, we have a system and we can do some cool stuff with it. And so today I'm going to be talking primarily about the first 2, because these are the first 2 things you need to do in order to get through the last couple of things. And then I'll touch briefly on the last 2 sort of towards the end of the talk. So let's first talk about representation. So as I mentioned before, boss encounters are tricky. How do we model boss encounters? I want to highlight the importance of picking an appropriate representation for this kind of problem, or for any problem where you're trying to procedurally generate an artifact in general. ideally, we want the representation we pick to be appropriate. And what does appropriate mean? Well, first, it needs to be expressive. So the space of all artifacts that we can generate things in needs to contain good artifacts, where good is something that we specify, but it needs to, whatever we define as good needs to exist in this space. In addition, we want our representation to also be restrictive. That is, in the space of things that can be generated, we don't want it to be overwhelmed with garbage. So for example, I could generate, if I were to generate the space of all moving 2D boxes, box simulations, that would be cool. There would probably be some boss fights in there, but there's a lot of things that aren't boss fights in that. So we want to make sure that whatever representation is, it allows us to prune the things that we are not necessarily interested in. And when we think about this, a good representation for bosses is not immediately obvious. So if we compare a representation for a very well-studied space like level generation, there are a lot of intuitive representations for levels. For example, you can represent a level as a tile map. So when you generate a tile map, visually you can see the things that it's generating. You're picking things. You're picking things to put in the tiles. This is a very intuitive and constructive way to think about the problem. But for bosses, it's not like that. And so we're going to do our best, but ideally our representation for bosses should align with how we as designers and developers think about boss encounters in games. So the first question then that we should probably ask is, how are bosses designed? And what goes into the design process for coming up with a boss? So I've talked to a lot of different game designers and developers about how they do bosses in their 2D action games. And some of the concepts that have come up are as follows. So typically bosses are designed around particular story moments. So often these are relevant to the narrative or to the story or to the progression. And so maybe you're killing your archenemy, or you're besieging something that will lead to further character growth or something like that. Bosses are also designed around environments. So things like the level they're in. So often designers or developers will think of a level that the player needs to go through, and then the enemies and the entities and the bosses and the challenges in that level will reflect properties of that level. So for example, let's say you have a lava level, well, maybe you would want to put lava monsters in the lava level and things that live near volcanoes. So things maybe like lizards as opposed to gerbils. And another thing that bosses are designed around are particularly the mechanics or the mechanics that the player has or recently acquired. So a game like Zelda is games like Zelda are particularly well known for this, which is in a Zelda game, you, the player, enter a dungeon, you acquire a new artifact, the challenges in the dungeon teach you how to use that artifact, and the boss fight at the end of the dungeon is a test to see whether or not you've learned how to use it properly. So this is how bosses are sometimes designed, but, or at least what goes into the thought process of designing a boss. So how are bosses implemented? So typically bosses are implemented in the engine of whatever game that they're being built in. Sometimes this is a low-level implementation, like directly in the general purpose programming language that you happen to be using, or it can be in a higher level scripting language. So maybe you have some sort of convenient thing that you've built in Lua on top of your C++ engine. In addition, the boss encounters require a lot of additional assets or special one-use pieces of music or art to be made, and there's also a lot of fine-tuning that goes into them. But let's take a step back again and note that bosses are typically implemented as pieces of code. So if bosses are implemented in code, then maybe an intuitive representation to think about would be to represent them in something that looks an awful lot like code. So for bosses, what we've done is we represent boss encounters as programs in a domain-specific language. So what I'm proposing here is that we come up with our own programming language to express all kinds of bosses in a particular space. And what goes into this programming language? Well, there are two parts. There's the things that we care about when it comes to thinking about boss encounters, which is the morphology. So there's all of these things that are declared as variables. So things like state, the boss's position, how big it is, how much damage it does, what are all these parameters, what are the special values for its speed and stuff like that. And the other part of our domain-specific language are a set of behaviors. These are domain-specific constructs, and these are expressed as function calls that allow us to specify properties about how the boss might behave. So what does this actually look like? So I'm going to walk very quickly through an example of a boss, and I'll show you how it's encoded in a domain-specific language. So here we have the Moldorm boss from The Legend of Zelda: A Link to the Past. And very quickly, this is a worm-like boss that moves around, and it's weak. It has a weak point on its tail. So on the left, we have a little picture of this Moldorm boss. And so in our domain-specific language, we're able to define, we specify some types and some properties and things we care about, like a physics object. And a physics object can be used to represent the head. It has a position, it has a velocity. And we can do something similar for the weak point. So we can say, oh, there's a hitbox on the weak point. And we can specify a lot of other broader parameters. So we specify this notion of health. So boss has health. It also has some values for speed, maybe some notion of invincibility time, maybe some notion of what team the player is on versus the boss. And so these are all the things that are related to a boss's morphology. And these are typically expressed as variable declarations with specific types that are unique to our particular domain. Next, we have behaviors. So I'm going to look specifically at the behavior of the boss's head. So here we have, I'm not going to go into too much detail about what everything that's going on, but Moldorm moves randomly around the arena, and so in this case, we're setting up these little, we're building these little graphs, or these finite state machines of its behavior from function calls in our language. So in our language, there's a function call called set random direction that takes some number for, which in this case is speed, and some other value, which is a velocity. And so we can use these to build these little functions to build up these finite state machines. And so here, if we run this, this is a behavior, it picks a random direction, and then it just goes in a random direction and changes, except now it's run off the screen. So to prevent it from running off the screen, there's other constructs in our language, like when it runs into the edge of a thing, reverse its velocity so that it will run around and, bonk the walls and stuff like that. And then we can continue to expand the graph and add things like, well, when it's hit by the player, we want it to briefly pause for a second, during which it has some invincibility frames. It will speed up and then run around a little bit faster. So then when we put it all together, we get something that looks like this. So this is an example of Moldorm encoded in a domain-specific language running in an engine that we've built for this. So you might ask, why a domain-specific languages? Programming languages sound kind of scary. And it's not the only option for this particular choice of sort of setup for a representation. The original implementation was something that looked an awful lot like a combinator library. Other things like affine grammars or operational logics would work as well as representation. But we argue that we like this idea of a domain-specific language because programming languages are an intuitive and expressive way for people to communicate with computers. And they're designed to be human understandable because it's really hard to program in low-level computer instructions. And there are also lots of tools out there for programming languages. And in many ways, thinking about programming language tools might help us to think about future design tools. The other thing is that we can leverage the properties of programming languages to inject designer knowledge and help constrain our generation. So we can help make things more expressive and also more restrictive by relying on well-studied concepts that come from programming languages. So specifically, boss design becomes programming language design. And a good boss design is encoded into the affordances of the language. So we determine, when we make this language, what good boss design might be. And this is where designer knowledge and designer intent is embedded into our system. And so ideally, a well-formed program in our domain-specific language should be a valid boss, and vice versa. And so very quickly, I'm going to run through an example of how programming language constructs can help us achieve this. So for those of you who've programmed, you're probably familiar with this idea of types. And so for primitives like numbers, there's different both the number 42 and the number 3.14 are numbers, but they're different kinds of numbers. In this case, integers and floating point numbers. And so both of these are numbers, and they belong to a broader set of things that can be added and multiplied and have arithmetic done on them. So we can do very similar things with types that we define. So now, instead of just relying on whatever primitive types our general purpose programming language provides us, we define our types. So now I've said, I'm in my language, I want to define this notion of a physics object, and anything that could be done to a physics object can also be done to its subtypes, like a boss object or a player object or an environment object. And the way this pans out when we start thinking about how to generate things is we have all these functions for behavior that I showed you before. So for example, let's look at this node that increases something. So in this case, it's increasing the movement speed by some number, which is 5.0. But ideally, we want to be able to reuse this and use it for any kind of number. And what are the kinds of numbers in our system? Well, there's this idea of jump speed, projectile speed, attack duration, weapon damage, maybe the number of patterns something takes. So, adding an attack pattern to a boss. And these are all different kinds of values. And the range of acceptable of appropriate values for each one of these numbers is different. So in a general purpose programming language, speed and duration might both be floating point numbers, but in our special language, they're different because they take on a different range of values. A 500 value might be very different for speed because it's a different set of units from duration and so on. So if we wanted to plug any number into this escalation and increase value node that I just showed you before, well, we could plug any of these in. But maybe we don't want to plug in health because that would be bad. So now what we can do is we can start customizing our domain-specific language to take these things into account. So now, both health and speed are numbers, but only speed and duration and damage can be escalated. Health can't be increased or escalated. And that will prevent us from accidentally increasing health, as shown in our example. So this is an example of how we're using sort of programming language theories and affordances to help us design the space of bosses. And what specifically, to reiterate, what specifically is going into a DSL like this is we give it a bunch of types. So this is fancy printed types from one of our implementations. So here we define a bunch of types. In addition, we define a bunch of function calls that represent the nodes and edges of these finite state machines that we use to construct boss behaviors. And this is effectively a spec for our language. So now that we have this language that we've built, how do we generate from it? And so just a quick overview, when you're thinking about a generative system, you start with some input, which is some representation that defines a generative space. You plug it into a generator, which is some kind of sampling algorithm that samples over that space with your favorite sampling technique. And then you get some generated artifacts as output. And so in our case, we have this domain-specific language, and we want it to spit out a valid program in our language, but what is the generation technique that goes in the middle? And so for our purposes, we've settled on using grammars. So we're working with a domain-specific language. It's a language. Languages are made up of grammars. It looks like a grammar. So as it turns out, for procedural content generation, generative grammars and grammar expansion have been used to generate all kinds of cool stuff in the past, interesting Twitter bots and interactive art pieces with tracery, the dungeons in Unexplored. These are both really good examples of how grammars have been used to generate all kinds of cool things, and I recommend you check both of these out. So in our case, typically in a system that uses grammar takes in a set of grammar rules is provided as input. There's a sampling algorithm, which is often just some form of random sampling or random expansion, and then it generates some kind of sentence in that grammar. In this case, we have a domain-specific language of boss encounters. We put it into what is now going to be a program generator, and it's going to generate us a valid program. And so I'm not going to have time to get into the technical details, but what we do is we take that domain-specific language that I showed you before, and we encode it as a context-free grammar. And in addition to providing the language, we also encode a set of production rules that describe how the pieces of the language can be expanded into programs. And then we just randomly expand the grammar. So using these production rules, we randomly select whenever we hit a production rule that should be expanded into a bigger part of the program, we just randomly pick one that fits. And this turns out to work really, really well. So what we do is first we start off by constructing the morphology and the state first, and then once we have all of that, then we use it to help build the structure of the behaviors and fill that in with all the values that we've picked. But as I mentioned before, we started with a context-free grammar, and now these behaviors and these functions need to reference bits of state, and that means that we're no longer context-free. So we have some extensions to context-free grammars in our system that help deal with this, which are in the paper that we wrote, which I will have a link to at the end of this talk if you're interested in looking at all of that. But to illustrate what I mean by this, so let's say that we are generating a behavior graph right now. We've decided we want this particular edge and we need to fill it in. So in this case, it's filled in with the tail of this Molder boss, and when the tail is hit by the player sword. But we need to be, when we're generating, we need to be able to fill this in with something random. You know, maybe we want a, we don't want to necessarily restrict it to the tail, but we want to restrict it to any physics object in the scene. So what are all the physics objects in the scene? Well, there's the physics objects that make up the boss, there's the walls, there's the player, and technically it could take all of these. So maybe it could be the case where when, you know, the wall is hit by the player sword, something happens in this boss behavior graph. Or maybe when the player hits itself, which sounds wrong. But then in this case, this is a place where we need to adjust our language accordingly. And as I showed you before, this is a place where we could potentially use subtypes to exclude the player from being inserted incorrectly into a behavior that we don't want. So now I'd like to show you a quick demo of our system in action. And this is a very intimidating picture, but I'll go through it really quickly. The details are not important. The domain that we're looking at for this particular demo is the domain of Mega Man-like bosses. So these are bosses that are typically about the same size as the player. They cycle between different kinds of attack patterns. So here we have 3 different attack patterns defined in this graph. And the boss rotates between the 3 of them. There's also some kind of escalation behavior on top of this. So when the boss gets damaged by something, probably on the player team, then it increments some parameters and the fight gets a little bit more difficult. Okay, so now I'm going to switch to a demo. And so I'm running this demo completely from scratch. I have no idea what it's going to show me today. Let's hope it doesn't break. And I'll do my best to explain it. So health is turned off because I want to be able to talk over this. In this case, I'm the little blue player that's hopping around right now. The boss is this orange rectangle that's trying to hit me. Oh, well, this is interesting. So at the beginning of the boss of the fight, So at the beginning of the fight, I launched a few shots at the boss and it was moving pretty slowly, but now it looks like one of its attacks is sped up considerably because after I hit it a certain amount of times with my bullets, its speed escalated. So if you see it zipping across the screen again, that's probably what was responsible for that. So this is one boss, you know, it fires some projectiles and charges at me, and it can stun lock me in a corner apparently. Okay, so here's another boss. This boss also seems to be able to jump, fire some bullets, bounce at me, be a little bit annoying. I've hit it a couple of times. It's continuing to... the player does not have invincibility frames right now, so this means I can get stun locked. Oops. Okay, well this is a little bit frustrating. But yeah, now it appears to have sped up considerably as I've hit it a little bit more. Let's see, here's another boss, more jumping. And the thing that I want to point out is that when we build the behaviors for this kind of boss, there's only one jump function that it can be using. But it's stringing these together to form combinations of different attacks, and it's putting in different parameters and picking these parameters currently randomly. So you can get all sorts of differences in the behavior. So when it's jumping at different heights, it's sometimes harder or easier, depending on your ability to dodge. So let's just generate one more boss. This one looks like it might have the bullets that hone into me, as well as bullets that don't hone in. And it's bouncing. Okay, and it looks like it's sped up. And that's kind of annoying. Okay, so that hopefully gave you a flavor of the kinds of bosses that we are generating in this particular domain. And this is the particular domain of Mega Man bosses, Mega Man-like bosses, but we've also tried to do this for domains like top-down 2D Zelda bosses, although the morphology for that is a little bit more complicated because now you want to generate bosses that have multiple parts in addition to having all sorts of complicated behaviors. So let's go back to the talk. So just a quick overview of what our current system looks like and what the process of building the system might be like if you, say, were to be interested in building a similar system of your own. So the first thing that went into this was, first we define a domain-specific language to express the kinds of bosses we want. So in this case I showed you Mega Man-like bosses, but it could be Zelda bosses, it could be Castlevania bosses, it could be bullet hell bosses. And the domain-specific language consists of types like health, speed, physics objects, values that are important to the mechanics of your game, and function calls that describe the behavior. So there's a jump function, there's a move function, and these can take different kinds of parameters, and you can get as specific or general as you like. The next thing that we do is obviously we're trying to make a game, so we need a game engine. And so what we have to do is we've written this domain-specific language, and so we need to build an interpreter on top of our game engine of choice that will read in these programs. So right now we have a system where I can give it the domain-specific language representation of Moldorm, and it should give me a Moldorm-like boss in my game engine. But now we actually want to do some generation, so we need a generator. And so in our case, we've implemented a context-free grammar expansion with a lot of modifications to handle those annoying variable references and state references that I mentioned before to generate boss programs. And the input into this is our domain-specific language, but also the production rules that are associated with how one might expand the language into a valid program. So what rules can we use to construct programs out of, given the types and the functions defined in our DSL? And for the curious, this is all implemented in F# and monogame, and at some point we plan to open source the generation code, so hopefully that will come soon. So we can generate bosses, and what comes next? Well, there's some, as I mentioned before, there's evaluation and cool stuff. So you're probably saying, well, that's great, but are these bosses any good? One of the big questions with any procedural content generation system is how good is the stuff that you're generating with it? So funny you should ask, because it's, how do you define good? And in the case of bosses, this is very, very difficult because there are a lot of things that make boss fights good. And as I mentioned before, a lot of these things are extremely subjective. So something good might be that the boss is beatable. So typically when we look at game-related artifacts and try to validate whether or not they're beatable, we can run static checks, or we can write an artificial agent to run through our, say, generated level to test whether or not the player can reach the end. But for a full, what is essentially a physics simulation, this is really, really hard. And so the techniques that we've used in the past for things like level generation may not necessarily apply to the kinds of things we're doing here. I want to point out that this kind of beatable checking or analysis is very similar to what we call dynamic analysis and software verification, which is really, really, really hard for non-trivial programs. And we have a non-trivial program here. It's a potentially infinite encounter with a bouncing physics object, which is pretty hard to verify, especially when it's not always clear what the win condition should be. Well, good might also mean fun. But the problem is players have different notions for what fun means. Often it's up to the designer to decide what is fun, given the context of the particular game. But there's a lot of these high-level concepts, things like challenge, a sense of fulfillment, gratification, empowerment, flow. And all of these are considerably difficult to quantify as heuristics. So as I mentioned before, we're randomly generating bosses, and we're randomly picking their behaviors and such. But it could be driven by some kind of heuristic search, but we need a heuristic, and an ideal heuristic might be one of these concepts of fun, but it's not clear how to quantify this. The boss fight might be intuitive, but again, what does intuitive mean? This is really hard, because a lot of us have been frustrated by bosses that are very difficult to beat, or it's not immediately obvious. And how do you encode this into a system like this? Or is the boss fight relevant to a context? Sometimes we play games and a boss fight will come out of seemingly nowhere, and it might seem unrelated to the rest of the game. And this brings up something that I mentioned very briefly before, and something that I've ignored for most of this talk because it's really, really hard, which is context and aesthetics for the boss are a really hard problem. So these typically boss fights are designed to be these climatic experiments that often tie into the story and have some very deep and important meaning to the progression of the game. But the truth is, we're still a long way off from generating something as emotionally compelling as Shadow of the Colossus, because it's not just the fight that makes this game a work of art. It's also the aesthetic and the context and the environment and everything about the moment that you're playing in the game that makes it compelling and interesting and exciting and fantastic. So anyway, this is still unsolved, and this is something that I'm thinking about. So if anybody has any ideas, I'd love to hear them, but we're still a long way off from stuff like this. So then the question is, well, where to next? I showed you a prototype, and the prototype is of little bouncing bosses running around, and this is something that I've wanted to make a game out of for a really long time, or there's a game that I've wanted to make that requires a system like this. And so that's sort of one of the next steps on my personal checklist for this kind of work. Other things that I think might be worth exploring are how could you use this as a design tool? So typically, there's a lot of effort that needs to go into making a boss. But could you use, given the mechanics of your game, and could you build a system that just lets you sort of randomly sample a set of bosses that might help inspire you to generate bosses of your own? And that's something that would be kind of fun if we could get it working. And then other things are exploring and generating other kinds of dynamic systems that could possibly be represented as domain-specific languages. I hypothesize that anything that involves generating some kind of behavior might work really well with our particular representation and means of generation. I would totally love a procedurally generated hamster simulation, which might turn into a future PROCJAM project. So that's all I have for you all today. And before I finish, I just want to throw out some thanks, particularly to my boss generating comrades in arms. So Eric Butler and Alexander Zook are my co-authors on the papers that we've written about this, and a lot of this boss craziness wouldn't have been possible without them. And also thanks to our advisors for letting us work on this stuff that wasn't related to our thesis. And also shout outs to the tons of cool people who have given us lots of awesome ideas. We've had wonderful conversations with folks in the AI and the indie community about work like this, and they've all been very interesting and fun and exciting, and it's helped to keep us motivated to work on this kind of stuff. So all of these wonderful people. I also want to give a really big shout out to all the people who are running PROCJAM, because, and I'm super excited to have been able to give this talk this year, and I hope you all enjoyed it. And there was a lot of work that went into organizing the jam every year, so shout outs to them as well. So to finish, if you haven't checked out anything about PROCJAM, there's a link to the info for PROCJAM this year. My contact info is listed here if anybody's interested in contacting me to talk about procedurally generated bosses or other indie stuff like Elsinore. And for those of you who might be interested in looking at the actual details behind all the stuff that I was talking about, here are the titles of the papers that we've written on this topic. So if you are interested in implementing something that looks kind of like this, helpful details are listed in there. So again, thanks very much for having me speak this year, and good luck with the rest of PROCJAM. Thanks.